Modern artificial neural networks require billions of parameters and thousands of layered operations to process basic sensory boundaries. Yet, a single living cell manages sophisticated signal filtering and adaptation entirely on its own. The inefficiency of artificial networks traces back to their core unit, the standard linear perceptron. These nodes simply sum up their incoming data and push it through a strictly monotonic activation function, like ReLU or a sigmoid curve. As the input increases, the output either rises or stays flat. That creates an immediate architectural roadblock. If you want a node to recognize a specific window of stimulus, meaning it fires at a medium input but turns off if the signal gets too intense, a single perceptron cannot do it. Engineers have to chain multiple layers of these linear nodes together just to force a boundary. Furthermore, linear accumulation makes networks vulnerable to oversaturation. When a massive data spike hits, the weights blow up, leading to catastrophic forgetting. We patch this flaw by stacking complex, computationally heavy normalization layers across the network. Relying on linear algebra restricts native adaptability. We are forced to build incredibly deep, energy-hungry structures to simulate the basic sensory regulation that a biological synapse performs natively. We can address this by shifting away from the linear perceptron. Instead, we compute activations using principles of thermodynamic equilibrium. This approach maps neural node mechanics directly to receptor states. Instead of relying on abstract weights, we constrain the mathematical boundaries using lab-measured biophysical constants, specifically the affinities of high and low state receptors. This leads to a new computational architecture, the Biophysical Recurrent Unit, or BRU. It separates the input tensor into two parallel calculating streams. The first is a state channel tracking internal saturation, and the second is an action channel determining the final output. Operating together, this setup gives the node native non-monotonicity. If the state channel detects oversaturation, it instantly restricts the action channel. Replacing linear algebra with thermodynamic equations changes the node's role. It stops acting as a static mathematical gate and begins modeling the dynamic transitions of a biological receptor. Let's break down exactly how the action stream works. It is driven by what biophysicist Richard Lanzara defined as the net shift equation. Rather than just asking if a stimulus is strong enough to trigger a threshold, the net shift equation calculates the net conformational change in a system's resting states across any given input dose. This chart plots output against input dose logarithmically, producing a symmetrical Gaussian bell curve. Because the equation is a rational quadratic, as the dose approaches infinity, squared terms in the denominator dominate. The output naturally decays to zero. This shape gives the action channel a native radial basis function. It defines an optimal window of activation without needing multiple layers to box the signal in. Because of its structure, it adheres to Weber's law. The node processes relative changes in a stimulus rather than absolute values. This built-in decay creates strict thermodynamic guardrails against exploding gradients. The node strictly conserves its mass, naturally capping its maximum output and eliminating the need for modern regularization layers. If this bell curve activation is so efficient, why isn't it the standard in modern deep learning? The reason lies in how neural networks train themselves. Purely non-monotonic functions are traditionally considered unstable for gradient descent. A threshold line reveals two possible input doses for any output below the peak, one low, one high. This 2-to-1 mapping confuses the optimizer during training. Worse, if initialized far right, the derivative drops to zero, backpropagation stalls, and the node permanently dies. That mathematical dead zone makes traditional gradient descent impossible for a pure net shift node, necessitating a structural intervention. This is exactly why the Biophysical Recurrent Unit incorporates its parallel context stream. It acts as a compass to guide the optimizer out of the gradient trap. The context stream calculates the sum of Langmuir binding functions. Unlike the net shift equation, the Langmuir sum tracks the total fractional occupancy of the system, counting how many receptors are bound to the input. Because it measures gross physical binding, it never decays. It is strictly monotonic. Overlaying the models, the Langmuir function forms a rising S-shaped curve slicing through the net shift bell curve. This one-to-one progression acts as a global positioning system. The ambiguous intersection points now map to separate, unique values on the Langmuir S-curve. Because the Langmuir slope never flattens out in the high-dose regions, it retains a strong directional derivative. It exerts a pulling force on the weights, dragging them out of the dead zones and back toward the peak. By evaluating the non-monotonic action channel alongside the monotonic context channel, the BRU circumvents the mapping trap without sacrificing biophysical realism. This dual-stream logic can be coded cleanly into PyTorch as a custom recurrent cell, splitting the forward pass to evaluate both equations simultaneously. But initializing this layer requires a specific approach. Dropping in randomized weights will instantly break the node, as it forces parameters to violate rigid thermodynamic boundaries. The affinity constants governing the physical receptors must be strictly positive. To keep backpropagation stable, we initialize these parameters in log space, spreading them across a wide, deliberate spectrum. From there, we deploy a gradient highway. During the first few epochs of training, we inject the Langmuir context gradient directly into the loss function. This forces the weights into the correct operational neighborhood on the curve. Once the network is oriented, we decay that auxiliary gradient to 0. Successfully instantiating this architecture requires replacing random initialization with structured biological priors. Arraying these units into a parallel layer changes how the system handles chaotic data. By log spacing the initial affinities across the entire layer, we create a multispectral adaptation topology. The nodes on the left are tuned to be hypersensitive to minute signals, while the nodes on the right are built with high capacities to endure massive intensities. Watch what happens when a disruptive data spike hits the system. The struct node's Langmuir state instantly registers the saturation. It dynamically downregulates its own receptor pool, collapsing its activation window and safely shutting itself off. Simultaneously, through a lateral kernel, the overloaded node shares a fraction of its saturation context with its immediate neighbors. This slightly raises their detection thresholds, preemptively shielding them from the spreading noise. In a traditional network, a localized spike requires the entire model to recalibrate thousands of weights via backward passes just to restabilize the loss landscape. Here, the adaptation occurs locally and dynamically in the forward pass. This thermodynamic shielding mechanism is precisely how a biological retina adjusts to look at a dim star right next to a bright moon without going blind. BRUs are not designed to replace the massive static layers inside large language models. They process complex math at every single node, significantly increasing the computational overhead per unit. The target domain is neuromorphic edge AI. When hardware must filter raw, noisy, streaming sensor data from the real world, the BRU provides extreme sensitivity and noise adaptation on a fraction of the power footprint. It is equally potent in reinforcement learning control loops. An agent navigating unpredictable physics requires RISC guardrails against environmental overshoots, and the thermodynamic boundaries of the node prevent the system from overcorrecting when inputs scale wildly. The engineering trade-off is clear. We surrender raw architectural simplicity and cheap arithmetic to gain optimization stability and real-time local sensory adaptation. We started with the rigid monotonic limits of the linear perceptron, a tool that requires deep layers of brute force to establish symbol boundaries. We addressed its blind spots by splitting the logic into an internal saturation context and dynamic action curve. The integration of thermodynamic principles shifts the focus from building static pattern matchers toward developing adaptive computational physics engines.